Okay, so if you already know some things about the situation, we can actually use this technique to make predictions about what will happen. Okay, so presume we throw a ball from a height of 6 feet upward in a direction of 60 feet per second. How high will the ball travel? Okay. My position function, we're assuming we're on Earth for hitting a ball. So we have our gravitation being negative 16t squared. I'm using this function, right? Negative 16t squared, that's the acceleration due to Earth. I actually know numbers for initial velocity, and I know numbers for initial position. So initial velocity is, I'm throwing the ball upward, so positive 60t from a height of 6 feet, so plus 6, right? Now, you could integrate and get this function, but since we've already integrated it, we can use those values right there, knowing that all projectile situations work the same way. So how high will the ball travel? We just want to find, this is a parabolic shape, so we just want to find its vertex. So I'm not going to graph it. It's probably be easier just to do the vertex as negative b over 2a, so negative 60 over negative 32. So 60 divided by 32 is 1.875, and s of 1.875 is negative 16 times that number squared plus 60 times that number plus 6.
Where does negative 60 over negative 32 come from?
I'm looking for a vertex, so negative b over 2a for vertex. Came from forever ago in algebra 2 or something, right? Yeah. Negative b over 2a for vertex. Again, you didn't have to do it that way. You could have graphed it and you calculated to find the vertex. I just figured I could do that faster than I can get my y equals and type that in and push all those buttons to get vertex. So that's why I chose that particular method. I thought it would be a little faster. So any method to find vertex, I don't care what method you used. Okay? So I'm just looking for vertex right here. And so you can say it really just asks how high will the ball travel. So it's going to have a max height of 62.25, what's it, feet? And you know what I just realized? I went back and used some really crazy algebra to figure that out, right? Why in the world did I use algebra to find the vertex when I could have used the critical value, right? Yeah, in the first derivative test. Would I get the same thing? Okay, what's its derivative? S prime of t is negative 32t plus 60, right? Where do you think negative b over 2a comes from? Because you got 2 times a when you did that derivative, right? And you're just going to subtract that over. It's going to be negative, and you're going to divide by this. That's where that comes from. So if you set that equal to 0, that gives you 32t equals negative 60. So t equals negative, well, 2 negatives, so positive 1.875. Okay, that's exactly where that comes from, is from the generic quadratic solution to its derivative. The 2 comes from the derivative, from the power. Pretty cool. Yeah, so way back in algebra even, you're learning these formulas. You're like, where in the world does all that come from? But it comes from the derivative as well, from a generalized form of the derivative. Okay, all right. Of course, that gives you the x-coordinate. If you want the actual height, you just plug it back in, the function. Okay, so that example is like one type of initial value problem. You have some initial values, like you start at 6 feet and you have a speed of 60. So you have initial values, those 2 being the initial values. That's not the only kind. So if I look at the next one, okay, so differential equations are equations like this one that have a derivative in them. So anytime you ever wrote down f prime of x equals, you were writing down a derivative, but also a differential equation. Cool. So a differential equation is anything that has a derivative in it, where your goal is to find the original function. And so the initial condition allows us to solve for a specific situation, so it allows us to find c. That's what we want to do here. Okay. So what you can kind of see in this particular graph is graphs of the antiderivative. I know the antiderivative is going to be sine or negative sine, something like that. And these are kind of what sine looks like, right? But this is a bunch of different signs. Like this one might be actual sine, whereas this one might be sine of x plus 1. They have those shifts, right? So this is the whole family of antiderivatives. And your goal is to figure out which specific antiderivative goes through that ordered pair, right? So find the value of c to make it go through that ordered pair. Okay, so we'll have the antiderivative y is equal to the antiderivative of cosine of x dx. Okay, so is the derivative of cosine positive or negative sine? Okay. Yeah, the derivative is negative, so the antiderivative is positive because they're opposites, right? The derivative of cosine is negative sines, the antiderivative is positive sine. So I have sine of x plus c, and so I know my ordered pair has us having 4 equals sine of 0 plus c, right? Because I'm plugging in x and y. And so in this case, sine of 0 is 0. So 4 equals c. So our specific answer with that initial value is y equals sine of x plus 4. And you can see that one graphed up here in the picture in a darker color because that is the specific one that goes to the ordered pair 0, 4. Okay, so just some thoughts because you guys are going to be super excited to take even more calculus. So calculus 2, like calc 1, I kind of said we're like just kind of touching into antiderivatives because in general there are lots and lots of rules. 60% of calc 2 is all about those rules, antidifferentiation. There is another 30, I guess 40, if I said 60, another 40% that's something else. Summations and series and other things, but most of it really is antiderivatives. Cool. And then maybe you saw a differential equation, like, oh yeah, differential equation, that wasn't so bad. There's a whole class called differential equations, right? So again, in general, differential equations can be pretty interesting to solve. So we're going to be able to solve the type right here that has the derivative by itself. That's pretty nice. But if you start throwing in things like y prime times y plus 2x y prime equals 7, and all of a sudden you need to solve that for the general antiderivative, then that's something that you would be doing in differential equations. It's got derivatives mixed with your x's and your y's, and you need to find what y is equal to in terms of x, not in terms of y prime. So there's like a lot of work. There are actually 3 classes on differential equations, 1 at the undergrad level and 2 at the grad level. You have differential equations, and you have partial differential equations, and then you have ordinary differential equations as well. Anyway, pretty interesting stuff, though, in that, in case you were interested. If you heard that word and you're like, ah, I've heard of differential equations before. It is its own subject matter, and it can be very difficult.
I had a friend whose favorite class.
Yeah, it's really kind of fun. But sometimes you don't even have a formula. Sometimes you just have, so like you have these graphs, and you just have like a shape of the graph, but you need to figure out what the original function was based on the shape of the pattern that you see, right? So differential equations solve flow patterns. So whether it's like airflow patterns, because you need to use like the pattern that it flows with to try to build up the pattern of the original function behind it. So that's their kind of story problems. Is instead of like how do you maximize how big an object is, you're trying to figure out how something flows through like a pipe or flows through a channel. So they work with flow a lot. Pretty cool. Okay. We'll get you excited to take some more math, hopefully. All these things you get to learn and find out. It's really cool. All right. What else are we working on here? Oh, last example. Let's just start over.